Is it open? Okay, I think we can start. So welcome to the second part of the session, the geodynamics of plate tectonics. And I repeat, the talks will be recorded. So the first talk is from Dennis Kent, and the title is Chasing the Late Jurassic APW Monster Shift in Ontario Kimberlites. And please.
I'd like to describe a unexpectedly large feature in the apparent polar wander path, the global one, that we had been discovered, and some attempts to try to verify the reality of this particular shift. And the discovery, so to speak, essentially is related to biased paleopoles and their removal. And one of the observations in any compilation of global paleomagnetic data, such as shown here, is that the data set is dominated by results from sedimentary rocks. And in particular, so this is from 40 to 260 million years, and you can see the relative proportions of sediment to igneous results. And in particular, this is going to be the focus is this interval right here between 120 and the bin between 120 and 160 million years that is particularly depauperate in igneous results and heavily weighted towards sedimentary results. And the problem with sedimentary results, at least potentially, is that there's a potential bias, something we call eye error or inclination error, that can be produced during deposition or compaction. And although this may be evidence of early acquisition of the magnetization, which is nice, but the directions may be biased to being shallow. It's sort of a well-known formula. It's been known for quite a number of years. And there's been some discussion of the reality of this effect, although it's more and more accepted that this actually does occur and actually might be quite prevalent. So for example, here in a sequence with sedimentary rocks and lava flows interbedded where there's no correlation issues, they're virtually the same age, we see that the results from red beds are shallower than those from the lavas. And the explanation in this case, and can be demonstrated using a technique to try to invert the data, try to determine the best flattening factor to correct them, shown here, is that you can bring these sedimentary results in very good congruence with the lavas, which we assume are a much more accurate representation of the ancient paleomagnetic or geomagnetic field. So if we take the approach then of removing all sedimentary results unless they've been corrected somehow with for inclination error directly, and then also collapsing, as I'll show you, results from igneous rocks from some large igneous provinces using updated ages, the resulting global database over this span is reduced to about a third of its former self, kind of very small. But the hope is it's more accurately represents the apparent polar wander path for the globally assembled continents at different times. And so this is the apparent polar wander path from global data. Essentially, we know the relative positions of the continents over this time, essentially a conventional Pangea fit, and then the opening history. So these are results from all different continents brought into a common reference frame, arbitrarily chose North America in this case. And what it shows is there's a drift. This is there's a time scale here for reference. This is essentially over the Triassic, drifting in a particular way steadily, and then it goes into a bit of a pause here from about 190 to 160 million years, and then this large shift, about 30 degrees, so-called monster shift, or I'll show, is really not apparent in any other apparent polar wander path, and try to explain why, and also provide some evidence of its reality. To this hook, very sharp cusp or hook in the apparent polar wander before going to the well-known still stand in the Cretaceous, at least the North American coordinates. So late Jurassic is the estimated age. So what I like to do is just show some examples of how the particular mean poles. These are in 20 million year bins, and this is in the center part. So here, at the end of this drift episode, at 200 million years, 180 million years, and then also here at 145 million years, how sort of an example of collapsing some data, also showing the basis of the mean poles. So here at about 200 million years, these results are dominated, in that window, are dominated by the Central Atlantic magmatic province, arguably one of the largest on the planet, encompasses 4 continents, and there's many, many results shown here in red. So one of the features of this, many of these have been dated, and this is a recent compilation of dates. And you can see the spread. The ones that are preferred still encompass something like 5–10 million years. But another view of this that many of us share is that camp is actually a very short interval, only about 500,000 years, and all the spread in ages is due to artifacts of the various dating attempts. All these are normal polarity, and this is the time scale derived from the Ewing Basin sequence, which we know quite well. So this best fits as being a particular of about 201 million years. And collapsing the results for the different continents, we have like a mega conglomerate test for the continents that the poles are much better grouped after accounting for the relative drift of the continents. Another large igneous province is this one, is the 183 million year Marfil-Karoo-Farrar Tasman, encompassing 4 different continents. The Karoo-Farrar Tasman has been known to be essentially very similar age. Again, the idea that many of these ages are artifacts, the spread in ages may be a consequence of just dating errors, is shown again here. It was done by Bob Duncan a few years ago. So the new dates are very much narrower compared to the 50 million year or so spread, and previously the paleopoles that went to various compilations essentially used the discrete ages and essentially spread the information over an inappropriate width of time. By the way, the Marfil, dating by Pankhurst, looks like this, and South America is part of this. So again, gives us a rather precisely dated and accurate, in terms of the paleomagnetic poles, accurate depiction of the pole for different continents. And these, again, shown if you correct for them, all these poles in their local coordinates collapse into a nice, well-defined mean, which we take to be a good representation of the field at that time with respect to the reference continent. And then finally, here is the last example before proceeding on to others items, is the 145 million year hook. In this case, we didn't take the average over 20 million years. We thought this was a distinctive enough feature characterized by these particular results, these Ithaca Kimberlites, Kimberlites in South Africa, and some dikes in Svalbard. All dated, you can see the dates, roughly about 145 million years, and again, giving a well-defined position when you adjust for the relative drift of the continents. So how does this, again, going back to, so I gave you these 3 examples, and now comparing it to other apparent polar wander paths shown here. This, again, is the one that I just described, filtered out just that was published a few years ago. If you would like the details, that filters out all the sedimentary results and includes just the igneous rocks adjusted as I described. And here's some well-known apparent polar wander paths, Besancordio, Torsvik, and others. And then this one just for North America, the so-called PEP, the paleomagnetic Eulipole. And you'll notice that these, the one that comes closest to at least describing the same geometry that we would advocate is the Besancordio, and then these others less and less. And basically it's a function that these other paths include more and more sedimentary data. So that, for example, in the Torsvik one and even the more recent one, there's something like 20 or 19 or so poles in the 160 million year pole, whereas we only have 4. All 19 are sedimentary, and they've probably been biased in various ways, not to mention many have come from the Colorado Plateau, which has rotations of still disputed amounts. So let me just try one effort that we did include in this paper with Ted Irving. This Lowmore and Upmore is the Morrison Formation. So this was the rocks that have some dates. They're in the late Jurassic, and should sort of plug this gap, or at least describe some aspect of it. We made an attempt to arbitrarily correct these for inclination error using some nominal flattening factor about 0.6, and also made an adjustment for the Colorado Plateau rotation, and this is where they would be. These are a reminder for those that thought about this in the past. The Morrison would once define this entire paleomagnetic Eulipole track in bygone eras, and the arrows show where the corrected positions would be. And the upper one comes reasonably close to where we think the correct position is. The lower one is questionable. This was probably a mistake to try to do this. But so what we attempted to do is find data of an igneous origin that could say something about this large gap of about 15 million years or so in reliable data. So we went to Kimberlites, one of the ones that we reported on before with Mickey Van Forsen years ago here in the Finger Lakes, and there's a similar group of them of similar age, at least here in Ontario, in the Kemaskaming area. And these have been dated, many of these have been dated with uranium lead. Do I have that backwards? Anyway, uranium lead perovskite ages. And two of them in particular, which I'll be describing here, those is triple B and the petty kimberlite, dated something like 154 million years, so somewhere between the 160 and the 145 million year positions that describes this very large shift. Here in Ontario, stable craton, pretty unremarkable place as far as expecting any disturbances, the field party. And this is, they're nice rocks, and from a paleomagnetic point of view, but they're a little hard to find, and they're pretty scrappy in the field. So this is next to a pit, as you can see, with the cattails growing. This is the outcrop and goes around back here, but not by much. So the sampling is rather restricted in many of these, and the results for this one is the date for this, more fully represented. So here's the paleomagnetic results. Basically magnetite. It doesn't matter if you do AF or thermal, very well grouped results. This is the preferred sampling tool in this part of the world, a backhoe and a few shovels. They have to essentially find these kimberlites, which were actually located by aeromagnetics and then drilled for diamonds, of all things. Again, very good, clear results. In this case, that they're reversely magnetized. And here's basically close to the bottom line. So here's the combined results from the petty and the triple B, and it falls more or less on, just the simple-minded, simple great circle path. It seems to fall virtually on top of this Cretaceous standstill, but with the normal reverse polarity and actually no basis for believing there's any remagnetization, and the normal polarity and the reverse there. It looks like we take this to be at face value what its age is. So this would suggest that there's at least we have a point that falls close to this particular join. And just to wrap up, is there any place else in the world that has directions of this type that haven't been already included in these joint paths? And this is a place in Adria. And here's the last slide. These are a series of results from sections done by Jim Channel, and here trying to put those in common coordinates. Basically the same kind of hook with a similar kind of shift seems to be there in an independent data set. So with these conclusions, it looks like there's some reality to this we call monster shift, 30 degrees in roughly 15 million years, with a plus or minus based on the age supplied by the kimberlites. And they are seeing these often neglected poles elsewhere, and these might mark perhaps the only sort of a good candidate for true polar wander in the last couple of 100 million years since the continental configurations can be described.
Is there time for one quick question? Any questions? Okay, thank you. Oh.
Has anybody tried calculating the change in the non-hydrostatic electricity with the movement of the plume has to make the Arcadius
I'm sure they have. I think Tron Torsvik has been using many of these apparent polar wander paths and true polar wander paths to do this to get some handle on some of the things you described, but I'm not that familiar with that.
Okay. That's great.
Okay, this is going to go yellow at 11 and red at 13, and then I'll stand up. Okay, and you have your pointer, yeah. Okay, you good?
Okay, thanks. So I would like to give a talk on continental collision and slab breakoff, show you some modeling results, and try to link them to some field observations. Before I forget, I'd like to acknowledge my co-workers on this and the funding agencies. Okay, so a typical example of continental collision is the one between Africa and Eurasia, which was closing the Tethys Ocean. It started off at 30 to 35 million years ago in the east and the west, and a bit later in between. Now, if you look at three horizontal cross-sections of seismic tomography, in this case by Spackman and Wortel, from 100, 115, 200 kilometers, you can clearly recognize the previously subducted Tethys Ocean along the rim of what is nowadays the Mediterranean Sea. So if you see here to the northeast, you've got the remnants of the Tethys Ocean's subducted slab, and in the south as well. There's a few gaps here and there. For example, here there's a gap which is related to what Max Smith was talking about this morning in his talk, and the volcanism over there. But if collision happened 35 million years ago, or a bit later at some points, and we can still see the slabs hanging in the mantle in tomography, then the question is, how long do these slabs actually remain there? Now, there's been some modeling work done on that. In the last 10 years or so, there's quite a number of groups that have worked on this. And the figure here on the left kind of shows you some results by the group by Taras Geria. And what it basically shows is that it's this slab breakoff, so the slab, the previously subducted oceanic plate sinking into the mantle, is a necking process. These are some slightly later results showing a similar result. Now, I would like to show a slight variation on these kind of models, based on the observation that if you look at the Mediterranean, in this case another tomography result at 600 kilometer depth, so just above the 660 discontinuity, we see that most of that previously subducted slab material is piling up there. And this vertical cross-section shows that the slabs which are still subducting, like at Calabria, and probably also all the previously subducted slabs, were supported from below. So they're clearly not hanging freely in the mantle, they're supported from below. And then, so the motivation for this work really is, can slabs that are supported from below, can they still break off? And if so, how long does it actually going to take? How long is it after collision that slabs do break off? And we're going to show you some three-dimensional calculations as well. So therefore, we would like to address the question whether slabs can actually show propagating tears, as has been suggested in cartoons like this one. So this is numerical model setup. I don't have time to go into all the details, but I use sitcom in both 2 dimensions and 3 dimensions, where we have a continental block embedded in an oceanic lithosphere, and that's colliding with another continent as the overriding plate. This is a little animation showing the principle of continental collision and slab breakoff. So we've got this continental block approaching the trench. And as soon as it hits the trench, then you will see that the velocities go down, the arrows get smaller, and then the slab is hanging there for a while before it actually shows necking over here. The slab breaks off, and that's the end really of the dynamics in these calculations. So these are 4 snapshots showing the same thing. It's the same calculation. So initially, the start of the calculation, complete collision, slab breakoff, and then the final stage. And the delay time between the very first collision, so the very first time that actually the 2 continental crusts are touching each other, and the final breakoff is about 17 million years in this calculation. The colors here show viscosity, so blue is strong and red is weak. The colors in this plot, which is exactly the same calculation but different coloring, is actually showing which is the dominant deformation mechanism in this calculation. So these calculations have done with several different mechanisms: diffusion creep, dislocation creep, a yield stress, yielding mechanism, and a maximum viscosity, which is mostly for technical reasons. Now, you can see that 2 things I would like to show you is, first of all, that during fast plate motion, like the ongoing subduction, we have dislocation creep in the shallowest mantle, as expected. But as things slow down and strain rates go down, then it's diffusion creep that starts to become dominant in blue. The other thing is that during the actual breakoff of the slab, the regime tends to be in the dislocation creep regime, which was a bit surprising. I expected actually the slab yielding mechanism to be responsible, but apparently the fact that the slabs are supported from below gives relatively small extensional or tensional stresses in the slab. So that's why the yielding mechanism is not operating. So the 17 million years of delay time between collision and breakoff is shown as this red dot over here. It turns out that if you do these calculations for different ages of the oceanic lithosphere, that actually this delay time is strongly dependent on the strength and therefore the age of the oceanic lithosphere, where young plates break off significantly earlier than old oceanic plates. And it's roughly a linear trend. This plot over here is from another group that did similar calculations showing qualitatively similar results. Now, one area where we can apply these results is the collision between Arabia and Eurasia. Shown in here, these are the present-day motions of this area, showing that the suture is kind of moving north, and we have here the Turkish area kind of moving counterclockwise, and kind of escape tectonics. Now, the reason I show you this here is that in this area, collision has been suggested to have started, occurred around 35 million years ago, and all the green papers that I show you here are suggestions of potential slab breakoff. Now, so they suggested several ages for slab breakoff. Now, only one of them can obviously be correct, because you cannot break the slab off more than once, but the model delay time between collision and breakoff for this old Tethys Ocean is on the order of 20 million years according to the model calculations I showed you. So this suggests that perhaps only the younger suggestions for slab breakoff are valid. And I have to add here that these suggestions, almost all of them based on flare-up of magmatism in the suture area. Another thing to point out here is that the North Anatolian Fold was initiated around 6 million years ago, and it was suggested by Fatsena and co-workers that perhaps this was due to a major reorganization of stresses in this area as a consequence of slab breakoff. And this again showed that if you take that model delay time between collision and slab breakoff, then indeed that seems to fit the data reasonably well in terms of timing, at least. So, okay, some three-dimensional calculations, which are interesting but a little bit more complicated to visualize. So what I'll show you here is some cross-sections right through the previously subducted oceanic plate. And this is a situation almost 16 million years after collision. And we start to see a little bit of a tear starting to form here. And then fairly rapidly, in a few million years, the tear is propagating from, in this case, the left to the right of the model. If we take these snapshots and the distance where the tear has propagated, we can calculate some propagation rates, in this case, about 300 kilometers per million years, or 30 centimeters per year, for this calculation. And again, these results are largely dependent on the strength and therefore the age of the previously subducted oceanic plates, where young, weak slabs, they break a lot faster, so the tear propagation is faster, whereas old plates are slower. Okay, so finally, a few slides on some very recent work that my PhD student Andy Botro has been doing. He looked at the effects of collision and slab breakoff on the topography of these regions. And there's several interesting results here, but I just decided to focus on just one. The fact that during continental collision, there seems to be a significant depression in the topography of the overriding plate. It seems to happen a few hundred kilometers away from the actual trench. And this is a temporary effect. So it's only happening for a while. And these are the plots I showed you before, the vertical cross sections of the calculation. And on top of that, you've got the topography, and the two lines are with and without filtering for elastic effects with the flexure equation. But they qualitatively show similar results. We've got this depression in the back arc region. This is another way of showing this. Horizontally, we've got distance. Vertically, we've got time. And colors here denote topography. Blue colors are low topography. Red colors are high topography. And again, the thing I was talking about here is this green, light blue area over here, which shows a temporary depression in the topography of the overriding plate. Again, we'd like to correlate these two possible observations in the geological record. This is a photograph taken by my colleague Mark Allen. It's taken here at the boundary between Iran and Turkey. What I would like you to focus on is this particular layer over here, which is a limestone layer, a Miocene limestone layer, which suggests that this has been deposited below sea level. Whereas this layer is actually sandwiched between two other layers, which are terrestrial red beds. So they're deposited above sea level. So this suggests that this area has been above sea level, then below sea level for a few million years, and then going back to above sea level. So suggesting a temporary depression in the topography. This limestone layer seems to be present more or less along most of the suture between Arabia and Eurasia. So perhaps there is a correlation between these two things. Finally, some work by Valentina Magni. She looked at the effect of continental collision and slab breakoff on the migration of the actual trench or the suture after collision. So normally we have trench rollback, as for example in the Mediterranean. Trench rollback meaning the trench is moving in the direction of the subducting plate. Whereas for several collision zones like Arabia, Eurasia, it looks like the trench is actually moving in advancing motion, so it's moving towards the overriding plate. And then as an example, Arabia, Eurasia has been moving for a few 100 million years. India, Eurasia has been moving for even more than that, maybe up to 1,000 kilometers or so in the direction of the overriding plate. And usually this advanced motion is suggested to be because of far field stresses, such as subducting slabs attached to the subducting plate, or far field mantle plumes or mantle drag underneath the plate. But what Valentina has been showing is that, in fact, if you have a model without any external forcing, you can actually also obtain that same result. And the reason is that slabs, which have a typical angle here during ongoing subduction, after collision, they tend to go towards a vertical motion. And this vertical, so the fact that the slab goes vertical is because of so it's rotating around a pivoting point somewhere in the middle of the slab. And everything above that pivoting point is moving towards the overriding plate, which could explain several hundred, or 200 kilometers or so of advanced plate motion. So to conclude, I think I need to wrap up, so I'll let you read the conclusions for yourself, but we've got some modeling results on continental collision that can be associated with observations for the Arabia-Eurasia collision. Thank you very much.
Time for one quick question. Claudia.
Sorry, a correlation between what and what? So the question is whether the weak zone in the model, I guess where between the overriding and the subducting plate, is correlated to the location of the depression in the models. It looks like there is no correlation between the two. So we tried all kind of different model calculations with different sizes of weak zones, and it looks like the depression is always roughly 300 kilometers or so behind the trench, so in the direction of the overriding plate. Well, we tried to look into this, and one possibility is the fact that the slab is actually steepening, sucking away material from underneath the overriding plate, and that could be responsible. And that would then be similar to the same results that have been shown for ongoing subduction, where mantle wedge flow is also dragging down the overriding plate by similar amounts. So that would be a similar result.
Okay, thank you.
Thanks, we have to move on, otherwise it can be too late. The next talk, this is the third one of the session, is from Luis Moresi, Betts, Wendy Mason, and the title is The Influence of a Mantle Plume Head on Subduction Zone Dynamics. Are you ready?
So we're going green.
There you go. And it'll go yellow at 11 and red at 13.
Okay, thank you. All right, I'd like to acknowledge my co-authors, Pete Betts, who's sort of a structural geologist and thinker of things Archean and Proterozoic, and Wendy Mason, who's a student who has been interested in some time in things which collide with subduction zones, and some work that we were doing recently on plateau collision led us to think about what happens when plumes and subduction zones interact. So the geological literature seems to be full of interpretation, at least, that requires plumes that should interact with subduction zones. And I've seen a lot of talks in which these things occur, and it seems a little strange to me sometimes that you should have convective upwellings and convective downwellings interacting so often. So I was somewhat uncomfortable with models which drew this as being a routine activity of subduction zones to interact with plumes, and I would look at, I'd look at where the subduction zones are and think, well, they're quite small as a target if you're coming up from quite a long way down. But of course, in reality, when you look at these subduction zones, they're actually migrating. Many of them are retreating across the mantle, and in doing so, of course, they're retreating with respect to the hotspot reference frame, and so they're going to start sweeping up stuff. And of course, they also sweep in everything from the plates as they move in towards the trench. So I was somewhat relieved to sort of realize that, in fact, the plumes don't have to always initiate near a subduction zone in order to interact with them. And it's an interesting problem in general, because one way or another, subduction zones will end up swallowing all of this debris that's sitting on top of the plates or underneath the plates. But I'm still not completely comfortable until I understand how to interpret cartoons that I see very often that look like this. And I shouldn't mean that cartoons inherently are something you should worry about, but this is an interpretation of some observations that we very often see. Convergent processes shortening in the overriding plate, followed by plume activity. And a simple explanation for that point of view is drawn in this way, that you somehow have a plume interacting with a slab that flattens it out. And then in order for the next part, for the plume to be expressed in the overriding plate, you have to detach the slab and you have to move forward. And after that, you have to sort of continue the subduction zone. And as we saw from Jeroen's talk, this is not a completely trivial operation to do either of these things, right? We actually, to detach a slab, we have to understand this is a simple thing to do in Adobe Illustrator. It's not so easy to do when it comes to actually understanding the mechanics. And I'm not trying to be disparaging here. I mean, it's very hard for me to look at this and understand everything that goes on. And so now I'm going to prove myself wrong, I hope, by showing you a plausible mechanism for allowing this to happen. So I'm going to break this up into two things. One is, of course, around the question of whether or not the buoyancy associated with a plume head or an ongoing plume is sufficient to sort of flatten out and detach a slab. And a slightly different set of experiments is whether or not you can then reinitiate a subduction zone in a relatively straightforward manner on the other side. So in other words, can we transfer the plume from one side of a subduction zone to the other side of a subduction zone and more or less continue business as usual? They just pass through each other. And I think there are ways one can do that. Here is another version of that cartoon. I should say this was an interpretation for Proterozoic terrain, which I'm afraid you can't really see very well from Central Australia. Here's a more recent example looking at trying to interpret Farallon subduction interacting with the Yellowstone hotspot. But it has the same story. It has the same story. So the plume is interacting with ongoing subduction. The subduction stops just long enough to let the plume get through and restarts again. Not entirely trivial. Now, I'm not questioning this model. I'm going to say, okay, well, I'll allow this model to exist if I can show a plausible mechanism that it can be done of how to do this. Then it's okay. So the two sets of models I'm going to show you, looking at each aspect of that question. The first one is a sort of a slab that rolls back across a buoyant anomaly. Here, these are all compositional models, so we're not dealing with the actual temperature evolution. We're just looking at relative buoyancy. So we're going to take an anomalous buoyancy associated with imagining a plume head, and we're going to allow a slab to roll back and counter it and see if it can go through. Second set of models I'm going to show you is actually associated with the second part of that question. Can we open a window in the slab with some buoyancy anomaly and then allow it to close back up again? And I have a slightly different set of models for that, which are actually more associated with opening the window in an easy fashion, so just making a gap a gap with some buoyancy, sort of a strength reduction that will create a window very effectively, and looking at whether we can close it again and how we would reinitiate that subduction zone on the far side. And that story is I do it in a wide slab, so it doesn't roll back. So I don't actually have in this particular case, I'm looking at sort of a static. The configuration's not changing very much until we open a slab window. So the first set of these results, let me just show you the sorts of things that happens. So let's sweep in some buoyant anomaly. Here it's marked by this red block. If we sweep in some buoyant anomaly into an ongoing subduction zone, we create a collision. If we run this without the buoyancy anomaly, then we see that this will continue for many thousands of kilometers of the slab going down, and we have a very, very slow retreat of the slab. But what happens in the case where we introduce some buoyancy anomaly is that we create a window and we go into advance where the anomaly hits, and we create slab retreat away from where that's happening. And that's basically to do with the fact that we've opened a window for the flow to go through. Okay. Let's look at how that works in a little more detail for a number of different models. Here, looking at whether the size of the plume is important. This is models that were published relatively recently, and these are for slabs that are rolling back. And so the case here, which has no additional buoyancy, is rolling back slowly in the center here. It's the light green one, and rolling back a little faster towards the edge. Okay, if we introduce a buoyant anomaly representing a plume, then depending how much stuff there is, we end up with a small amount of trench advance associated with the point where the buoyancy arrives, and we have continued retreat elsewhere. In fact, the rest of the subduction zone can barely see the fact that this collision has occurred. Okay, so what we have is that this particular part advances quickly, the window opens, and we create this distinctive shape in which we have advance and retreat going together. Sorry, the yellow one is virtually invisible, but it's another extreme case, the largest diameter plume head that we put into it. Let me interpret that model for you in a cartoon of my own. This is what I think is then happening in these models, that we have some buoyancy anomaly. It's being swept into the subduction zone in this case, and the subduction zone is rolling back over it. As it collides with the subduction zone, we get this zone of crustal shortening associated with the advance. It's very much a local effect, however, and we get a slab window. The slab window is what allows the plume material to pass through from one plate to the other, and then we go to section C. Now we have an ongoing subduction system, and we have a gap. And the question is, can we now re-establish this subduction system behind the plume and allow the plume to pass through, essentially undisturbed, through a subduction zone? And here is a model which shows how that happens, in my view. So here we have exactly the convergence that we're talking about. Here is a buoyant anomaly. It's not really intended to be either a plume head or a plateau or anything in particular. It's a buoyant anomaly embedded here in the plate. So I'm not saying anything about where it comes from. It's in what would otherwise be a static environment. And you can see that, in fact, there is a way for this window to close. It's not as simple as I thought it might be, but what happens is that because this arc then begins to curve around, you are able to sort of roll back in two directions, and roll back in this direction as well, and at some point this causes the collapse of this window, and it slams shut quite fast, actually, just by reinitiating along this edge, tearing downwards, and beginning to subduct again. You'll also see that there's this material now suddenly goes from compression to extension as the subduction zone restarts. I'm just going to show you without the overriding plate traces there, so that you can see what happens. This is quite a small anomaly that's gone in, causes a relatively large window, and it closes like a curtain. It swings across rather than reinitiating a sudden point. It closes by sort of rolling back a little bit at a time, which is the mechanism I didn't intuitively realize would happen. Okay, to summarize, well, I think the interaction of plumes and plateaus is not uncommon in how people interpret the geological record, at least. And I've shown you sort of a plausibility argument of a mechanism in which a plume can cut through a slab. It's only a plausibility argument. I haven't done enough models, fairly complicated. I haven't done enough to parameterize this carefully. I only have 2 or 3 examples to show. But it is possible in at least one of those models to form a slab window which the plume can pass through and close that window again. I've shown how both those things can occur. The slab window has some opening that slab window has some observable consequences. One, of course, is that there's a hole in the slab, but also it's a shortcut for flow, so suddenly it produces localized rollback even when there wasn't any before, produces a strong curvature of the trench, compression and rotation in the upper plate, and when it closes, it slams shut. All right, thank you very much.
Is there a question? Yeah, Alan.
These models, it looks like the buoyancy is embedded in the plate itself.
Yeah, I've done that.
Models where it's clean.
The first set of models I showed, did anyone want me to repeat that? The second set of models have buoyancy embedded in the plate. The first set of models, it's actually underneath. And the reason for doing that is to allow, in one case, is to allow the window to develop all by itself, and in the second case is to force it to open so I can shut it again neatly. I mean, and of course, the next thing is to combine those.
Norm.
With the Columbia basalts, there's a plume head, but a relatively small one that has a sudden bend, so the slab may have beheaded the plume tail at a considerable depth, and the beheaded plume tail is going to still be buoyant, and they come up the bottom side of the slab and produce the hot spots like Cobb and Bowie that are fairly long lip, and that's kind of something else. The model, there seems to be a hiatus of our volcanism sometime before 60 million years, which is the usual argument for the slab temporarily going flat.
Yeah.
The buoyancy of a 10 billion-year-old slab and the buoyant swell are about the same. So it's
Okay, did you have a response to that?
I can make the only comment I make is that when we do put small buoyancy anomalies on the underside of the plate, we do get the opposite behavior, which is that they don't necessarily have to go through. Yeah.
Okay.
Yeah. That's right.
Okay, thank you.
Thanks. Ready? We proceed to the fourth talk of the second session, and from William Buck. The title is Implications of Plume Head Feeding of Asthenosphere for Continental Breakup and Convergence. This is also an invited talk.
Which one is it? It's this one's a little bit later. Yeah, it's a little smaller. Is it smaller? Well, it's good. Let's see what you got. Okay, it's 13 minutes till the red goes on.
Okay,
it
good.
goes on at yellow goes on at 11.
11, okay.
And it's a black button, so it's hard
So
to
is it longer for you invited, or is it?
No, it's the same.
Oh, same. Okay, good. Okay. All right, thanks very much. So we're going to continue the theme of thinking about the asthenosphere, and I'm going to go through several processes where the asthenosphere may be important, and say, first of all, that I'm going to start with kind of a very accepted view about how plume heads might help initiate rifting. It's not very controversial, and say that this used to be my only real view about the lithosphere, about the asthenosphere, about the role of the asthenosphere, of low density, very hot asthenosphere in affecting plate tectonics. But I've become a convert to this kind of radical idea that was first put forward by Jason Morgan 40 years ago, I think, that perhaps the asthenosphere is actually everywhere, maybe not quite as hot as plume heads, but still hotter than the underlying mantle. And I'm going to go through a few sets of observations very quickly, actually, that led me to sort of change my view to a more radical view, or maybe more the Phipps-Morgan camp. And then finally, talk about a kind of crazy application, not just to plume heads thickening asthenosphere, but perhaps getting relative thickness variations behind and in front of subducting regions. Okay, so it's been accepted for a long time that at least 30 years that active rifting or plumes are correlated in time with, or at least the effect of plumes, large igneous provinces, are related in space and time to major rifting events. And this very nice compilation from 10 years ago or so shows that typically the large igneous provinces have dates that predate by a few to quite a long, many millions of years, the onset of seafloor spreading in different areas. So most areas where continents rift apart are large igneous province areas, and I think the standard model of the development of large igneous provinces involves plume heads. And just a quick look at some data. This is some beautiful data from off of Argentina showing seaward dipping reflectors and covered by more recent sediments, but lava flows, and then interpretations, kind of a general idealized view of many of these margins that are affected on land with large igneous provinces have huge thicknesses of basaltic material. So the usual view has been that from way back, from ideas about active rifting to laboratory experiments to calculations about uplift and degree of extension, that it's not unreasonable to get kilometer scale, half a kilometer to 2 kilometers of uplift and considerable extension over a plume head, and extensional stresses similar to ridge push sort of forces, 3 to 5 times 10 to the 12 newtons per meter. But one thing that I weighed in on this was to think about the effect of the melt itself, and I think some of the early papers assumed that if there's melt around, it would be able to cut through the lithosphere and essentially accommodate extension. And I've claimed that, in fact, it takes fairly large stress and that areas of extremely thick lithosphere can't very easily split apart even if there is a lot of magma. But one thing about what I would call magmatic rifts is a lot of them are straight. They seem to be centrally fed up and down the Arabian side of the Red Sea. In some places in the Egyptian side in Sinai, you'll find dikes that only slightly postdate the major trap event, plateau-forming event in Ethiopia and Yemen. And rifts also cut regions of old, stable platforms, but actually seldom cratons. It's interesting. So the straightness is probably the central feeding, and not just following pre-existing weak zones, which you'd expect for tectonic rifts. And if you calculate very simply the standard sort of Brace and Kolstad approach to thinking about stress differences for tectonic rifting, where you extend, you pull hard enough to get normal faults, the yield stress depends on a friction coefficient, and the difference in the sort of horizontal stress has to be lowered a huge amount at depth to accommodate slip or to produce shear fault slip. But the intrusion of a magma-filled crack actually depends more on the density contrast between the magma and the surrounding rock. This is under the assumption that the cracks, when they get to the surface, can have excess pressure. They'll spread out at the surface. And the stress differences, certainly for crustal rocks, can be very small. For mantle rocks, if you're cutting through fairly strong mantle, there's a fairly sizable but still much smaller stress difference than required for shear faulting. And so you can go through an exercise and say, okay, for lithospheric thicknesses with reasonable crustal thicknesses, that the tectonic rifting requires huge forces. This is sort of saying that might be the upper limit on what we could have available. It's a bit disputable, but it clearly shows that magmatic rifting, defined the way I did in the slide before, could happen at considerably lower average force levels, but still areas that are extremely thick probably can't rift. So it's not surprising that Tanzanian craton is split by or it splits the East African rift, moves around it, doesn't cut through it. And the same thing is in the north of the Red Sea, that it can't propagate into old oceanic lithosphere. So old oceanic lithosphere should have lithosphere that's thick, and actually it's also hurt by the fact that it has very little low-density crust. And so my sort of overall synoptic view of stretching is that there's basically two ways to get stretching. And if you have normal lithosphere, you probably can't tectonically stretch it. So areas like East Africa sat around since Pan-African times not doing anything, got quite old and cold, and not until the Ethiopian basalts came along were they cut by basaltic dikes and able to split apart. And of course the other way is if you have orogenic lithosphere, like the western U.S., that's thick crust and quite hot, yield stresses could be small enough and yield forces could be small enough. to have these areas extend under their own weight, essentially. But there's one problem. Every indication is that the main phase of active magmatism, at least the part that produces the large igneous provinces, as mentioned by Dennis Kent, better and better dating indicates that this occurs over a very short period. And so we've worried about this, and a couple of students of mine worried about just 2D cross-sectional models, the idea that we'd shoot dikes through them. And I don't have time to go into these, but these were basically taking normal lithosphere, shooting dikes through in a very self-consistent way in terms of their vertical extent and related to the stress field present, and never letting the sort of driving force ever exceed a certain amount. So they were kind of involved calculations. They're published. I think we did this in JGR. And the key takeaway message that's not, well, it's shown here in just time, but actually what we found out was that only about 2 kilometers of magmatic accommodation of spreading could weaken the lithosphere significantly or sufficiently that actually the stress would drop down even if we didn't put in dikes. So each one of these little ups and downs was actually a model dike being put in. And they never weakened things until we got about 2 kilometers of extension. We started with a sort of a typical platform geotherm. So it doesn't take unreasonable quantities, much less magma, even over the several thousand kilometers extent of some of these rifts. It's less volume of magma than we see at the surface. It needs to be intruded to greatly weaken these areas and have them continue to spread at moderate stress. All right, now, one step more speculative than this is this idea, going back to Morgan's earliest papers about plumes, was a suggestion that plumes actually fed an area of lithosphere that was constantly being fed by plume heads and plumes and didn't cool super fast. And here's a sort of simple picture from Phipps Morgan and his student Maya Yale, suggesting that there might be a layer that's a little bit less dense than the rest of the mesosphere. And I never liked this idea because it complicates the picture of the mantle. But the reason I started to like it was because of Chris Small. So Chris Small kept showing me this data. So this is just bathymetry for the Pacific, that Chris picked a color scale for depths to sort of accentuate the difference in depth between the East Pacific Rise and the Pacific Antarctic Ridge. And the East Pacific Rise, as most people know, is the fastest spreading mid-ocean ridge, and it's also the deepest mid-ocean ridge. And Chris averaged data within 50 kilometers of the spreading axis up and down this system and showed that essentially the EPR is about 400 meters deeper than the Pacific Antarctic. And just going very quickly, this is a paper from some calculations where we put a low-density asthenospheric layer over the rest of the mantle and drove the deformation in that layer by essentially couette flow driven by slabs moving and Poiseuille flow back. And the bottom line was what was on the slide before, was this little dashed line was from a very crude 3D model of the Pacific, well, really a 2D thin layer model, plan view model, but with fairly reasonable values for viscosity and thickness of the asthenospheric layer, we could fit the shape of this anomaly, and no one else has come up with a good explanation that I know of. Most sort of global dynamic models for the Earth give the EPR making it the shallowest ridge, not the deepest ridge. And then we got interested in the deepest spot anywhere on the ridge system is the Australian Antarctic Discordance, and this is in a paper out a few years ago. We used the same parameters, but we had Australia and Antarctica were taken to have thick cratonic roots, and asthenosphere had to flow around it. And anyway, this is just a total depth plot from a simple model. And then again, this dashed line compared to data along the ridge matches essentially the wavelength and amplitude of the depth anomaly there. And then one other application was interesting. A colleague of mine, Torsten Nagel, published a paper 5 years ago looking at some data similar to what Louis Moracy was just showing, and we're very worried about the fact that you have trench advance in the west and trench retreat in the Pacific. And he worried about how a buoyant asthenospheric layer might produce this, and then just racing through with that kind of schematic model of a flow field. Here's the data on advance and retreat of the Pacific slab, and here's models for slightly different parameters. So it fits the trend. And so the most controversial part of this is that I'm claiming that that you need plume heads to get extension, that it looks like you may need an asthenospheric layer to explain large-scale depth anomalies in the oceans, where I would say it's the simplest place to look at what's producing depth anomalies. And then last of all, very quickly, just suggest that you need, of course, huge forces to make mountains, and one simple way to get them actually involves the asthenosphere. And so just very quickly, low-density crust that's pushed together and thickened to a mountain belt. If you take scales from mountain belts, you need something like 5, 6, or 7 teranewtons, or 10 to the 12 newtons per meter. And using the kind of asthenospheric thicknesses we did to look at the Pacific and the Australian and Arctic discordance, but under the idea that a very long-term subduction would essentially plate on asthenosphere and take it out of the system, you could eventually thin the asthenosphere, giving you a contrast in thickness that would cause compression, and the amounts of compression for reasonable layers of thickness can be quite large, even though density contrasts, temperature differences might just be 100 or 200 degrees. Density difference is very small, but length scales being large, coming in a quadratic way, you can get kind of large levels of compressive force. And a little sort of simplistic model thinking about not only force balance but torque balance would say that as you get this kind of contrast, you could get shallower dip slabs, and I put together a little analog model, and I won't go through a picture of it, but just basically taking water out over corn syrup with a slab here, aluminum slab here, can give you a picture. Once you thin the layer of asthenosphere, you can actually get low dip slab subduction. So in conclusion, plate motion-driven thinning of buoyant asthenosphere may explain depth anomalies over spreading centers that haven't been explained at least in the East Pacific Rise. Certainly there are other suggestions for the AAD related to subduction zones, old subduction zones. It may relate to mountain building, low dips of slabs under mountains, and then I didn't get to talk about orogenic collapse. If you sort of open up a slab window in one of these models, all the low density asthenosphere sort of pours into the area of asthenospheric thinning and sort of promotes collapse. Thanks very much.
Okay, one quick question.
I thought Norm would give me one.
A quick question.
The asthenosphere thing will also occur without flow, just from the mantle being heated from within, and the thermal gradient is going to be sub-adiabatic, but will occur enough for you to have the effects, I don't know.
I'm not sure either.
Yeah, but you'll get that effect even if there were no plumes, which are certainly haven't yet emitted that cap for over 20 years.
Thanks very much.
Okay, let's proceed to the next talk. We begin by Megan Miller and Thorsten Becker, and the title is Deflection of Mantle Flow Controlled by Slab-cratonic Keel Interactions, Insights from Shear-wave Splitting in the Southeast Caribbean.
This is also going to be 11 minutes to yellow and 13 minutes to red.
Okay. All right. So today I was going to talk about the Southeast Caribbean. Torsten and I have been interested in the interaction between subducted slab and keels, and this is a really good area to investigate it because we have the subducting Antilles slab along the Caribbean arc, and the South American craton is very close to the plate boundary between the Caribbean and South America. So just a quick overview about the evolution, tectonic evolution of the Caribbean plate boundary. This is a very simplified cartoon of reconstruction over the past 90 million years. So here we're showing, this is the 90 million years and the time progressing to the right. So basically the story is that there's been rollback of the Caribbean plate and arc in this direction along the northern margin of the South American plate. And along this northern margin here, over the past about 55 million years, has been development of the El Pilar strike-slip system. It's been active for about 55 million years. So here's a generalized tectonic and seismic array map. Over the past 10 years or so, there's been extensive new seismic deployments. Part of it was part of the Bolivar experiment, which was funded by Continental Dynamics program. We had a combination of broadband, both OBSs, which are shown here in the hexagons, as well as on-land broadband seismometers are shown in the triangles. Some of the other important features that I wanted to show, to point out in the region, of course, is the San Sebastian El Pilar fault system, which is the plate boundary between the Caribbean plate and the South American plate. It's a right lateral strike slip system. Of course, there's also the Antilles subduction zone here. And the other thing that's really important about the region to realize is that the Atlantic plate that's subducting beneath the Antilles Island arc is actually part of the South American plate. So this oceanic lithosphere is subducting here, but this is actually connected to the South American continental plate here. And the basic surface expression of the continental keel is here in the Guyana shield. So you can see that the craton is very, very close to this plate boundary and to this active subduction zone. So using these 100 or so broadband stations, there's been SKS and SKKS splitting measurements done over the past 10 to 15 million years. This is a compilation of results from the Bolivar experiment as well as earlier ones. The scale here shows the delay time, which is about 1.5 seconds. And many of the splits in the region are much larger than this 1.5 seconds. And the global average, to give you a context, is about 1.4 seconds or so. So they're much larger than the global average. And they're essentially many of them are essentially parallel to the plate boundary between the Caribbean and the South American plate. And of course, SKS measurements are quite good for understanding seismic anisotropy because you can infer lattice preferred orientation of olivine in the mantle. So here's a lithospheric model, conceptual model with seismicity. This model is put together by using a whole bunch of different seismic observations, surface wave tomography, receiver functions, active source, there's onshore, offshore active source profiles, also part of the Bolivar experiment. So we put all this data together to come up with a conceptual model of what was going on. This surface here is showing the moho, so we've taken off the crust, so there's no crust shown here. This is the continental lithosphere. This is a view basically from the northwest to the southeast, so north is in this direction here. Here's the subducting oceanic lithosphere beneath the Antilles Island arc. So here's the islands here. Here's Trinidad for reference. And we're also not showing the Caribbean plate. So we can see the subducting oceanic lithosphere, the continental lithosphere of South America, and then this gray surface is the projection of the El Pilar San Sebastian fault system projected vertically to depth. So what we thought was going on in the model, or in the tectonic history, is as the subducting oceanic lithosphere was rolling back, and we saw in the cartoon that I showed earlier, it's rolling back along the El Pilar fault system, developing this fault system. But it's really the oceanic lithosphere is tearing away from the continental lithosphere, and the expression of that right now is this paria cluster of seismicity. So you see this pipe of seismicity in the corner between the oceanic lithosphere and the continental lithosphere, showing where there's active tearing going on. So from the seismic results, what we thought was happening to help explain these large splitting anomalies, shear wave splitting anomalies that we saw near the plate boundary, as this plate was rolling back, mantle flow was coming around the corner in a toroidal sense right near where the current tear location is going on. So we had this conceptual model based on seismic results, but we wanted to do some geodynamic modeling to see if that was really the case. So what Torsten and I did, we did global circulation models. These are instantaneous models using SITCOM-S. We have a rheology based on layered viscosity structure, but also with layered lateral viscosity variations. We assign the plate boundaries to be weak, low velocity zones. We also assign the density anomalies based on simple scaling of velocity anomalies for both P and S wave tomography. And we also assigned Wadati-Benioff zones for slabs. So we put in the slabs based on Wadati-Benioff zone seismicity. And in these models, we have about 20 kilometers resolution globally. Okay, so once we run these global models, we're then able to predict the shear wave splitting in a quantitative way. So we can infer the lattice preferred orientation of olivine from the mantle flow models following the DREX method of Kaminsky and also Becker in 2008. And then we compute the synthetic splitting computed using full waveforms incorporating finite frequency effects. So we use the combination of all the events that that were used to make this compilation of shear wave splitting measurements. And so we have the exact event station locations, predict the splitting for what those would be for each event at each of those stations. And if we have the back azimuth information as well, we also take that into account. And so we actually ran 176 different geodynamic models to explore the different viscosity and density structures that could explain the splitting measurements that we observed. So this is how we were testing the strong seismic anisotropy and how it's developed through time. So I'm not going to show all 176 models. I'll just show 4 that kind of show the highlight what we found. So this is the SMEAN model. So this is the Mantle viscosity structure input, and this is our reference model. So from here on out, I'm going to say SMEAN is a reference model, and SMEAN is a long wavelength shear wave composite model. Our second model is adding slabs to the SMEAN model. So we're putting in slabs based on Wadati-Benioff zones. So you can see the Caribbean one here, South American, of course, in the Western Pacific. And then we also, for our third model, we also incorporated a weaker asthenosphere. So this asthenosphere is between 100 and 300 kilometers depth, but just beneath the ocean. So you can clearly see the red here in the viscosity plots. And then finally, for our preferred model, we have the SMEAN model with the slabs based on Wadati-Benioff zone seismicity, the weaker asthenosphere beneath the oceans, and also put in the keels. So we put in the keels globally based on the 3-SMAC model, which is based on geologic mapping of where the continental cratons are located. So you can see the South American craton located here, of course, the North American craton, and so on. And these are slices at 165 kilometers depth. Okay, so this is our reference model. So we're just zooming in. Although these are global models, I'm just going to zoom into the southeastern Caribbean. This is showing the observations for SKS splitting are shown in the colored bars. So these are the ones I showed before that were shown in orange. And then they're colored by the angular misfit between the fast axis in the predicted splits, and the predicted splits are shown in these white and gray bars here. So what the colors are showing is basically when you have a good misfit, they're blue. When it's a bad misfit, they're red in terms of angular misfit. And then the delay time misfit are shown here, the averages. So when they're over-predicted, then it'll be a positive value. So if you get a larger delay time than expected. So for our reference model, which is using SMEAN, we don't get a very good fit between the observations and the predictions, although they're not bad here. So if we add the subducted slabs, we get a much better fit. So of course we get the slab here beneath the Caribbean, but also globally as well. And so we start to improve the misfit. It's much decreased here. So this is the back azimuth variation for each of these stations, but this is a global one here. So it starts to improve. For our third model, where we put in a weaker asthenosphere beneath the oceans, it matches a bit better in some regions, but others not so well at all. So that was a bit disappointing. So we have this is with the slabs, the weaker asthenosphere beneath the oceans. But then if we add the continental keels, we get a really good match between the observations and the predictions. So most things are blue and green, and this is very good compared even to the San Andreas in the western U.S., where this has also been done. And then Torsten gave a talk on Monday looking at AFAR and the Middle East, and this is much higher than they've gotten so far on that work which is in progress. Okay, so if we now know that you need keels, you need a weaker asthenosphere, of course you need the slabs, but what's going on in the mantle flow? So if we look at the flow generated with and without keels, so this is just with the weaker asthenosphere, this is the weaker asthenosphere plus keels at different depth slices at 75 kilometers depth, 165, and 435. You can clearly see subduction going on along beneath the Caribbean arc. But it's not a big difference, but it's what's most important is looking at 165. You see that the flow is basically north-south beneath the continental South America. This is the El Pilar Fault zone right here, just for reference. And if we look at the one with the keels, you just see that they're very slightly deflected. So the flow is really slow here, but it's just this deflection from north-south to going around to a southwestern direction that actually makes the match between the predicted splits and the observations. And then below the keels at 435 kilometers depth, it returns to this basically north-south orientation, which we see both with and without the keels. Okay, and we can check this by looking at the plate motion. So the predicted versus GPS is a compilation of GPS measurements. And you can see that for our reference model, it's not very good. With the slabs, it's also not very good. Add the Asthenosphere, it starts to be a bit better. And then here's our final best model with the Asthenosphere plus keels. We overpredict the velocity of the Caribbean plate, which is about 2 centimeters per year, but we still get the orientations to be quite good. And we can also show you those matrices that we put together of all 176 models. Here's our preferred model here with the weaker Asthenosphere, the slabs based on the rum contours, and the keels. But you can see all the different viscosity variations that we tried, also, and the average misfit for each of these in terms of the angular misfit. Here's all the different density structures. So we tried different tomography models, the MIT model, some other regional ones that we embedded in SMEAN, for example. Okay, and then if we look at the regional delay time misfit, here again is our preferred model. It's nearly zero, so we're getting very good misfit in the delay times. And if we look at the global velocity correlations, not just the regional one, but the velocity one, we also get a very good match with the global plate velocities. Okay, so in conclusion, we get what we need to be able to fit these very strange large splits along the southeastern Caribbean. We need a weaker Asthenosphere between 100 and 300 kilometers depth. We need to accurately input the lithospheric thickness, put in the slab morphologies, but we really need the stiff keels. And Matt Fouch had suggested this in 2000. So this is able to match the regional delay time, the angular orientation, and also global and regional plate velocities. And if you want more information, this paper just came out a couple months ago in Nature Geoscience, and this was funded by NSF for both of our career grants. I'm happy to take questions. Thanks.
Time for one quick question. Okay, thanks.
Okay, we can proceed. Next talk is given by John Naribov. Co-authors are Billen, Geria, and Saunders. The title is Numerical Modeling of Outer Rise Deformation in the Tonga Subduction System, Coupling between Outer Rise Deformation, Slab Weakening, and Plate Velocities. Please. John, I know how to work.
Yeah, it's okay. It's a black button right there. It's going to be, it counts down from 13. And when it gets to 2, then it'll go yellow and red.
All right, well, thanks to the conveners for giving me the chance to present this information and some of the results of our work. What we're going to be talking about today is the effect of bending stresses on the development of normal faults and subsequent slab weakening in the outer rise portion of subduction systems. So first, a quick overview of outer rise faulting. This is a very nice conceptual model of how outer rise faults develop and then are subsequently subducted down through the trench from Narrow et al. 2005. So what happens as the slab bends beneath the overriding plate, you get extensional bending stresses and normal faults develop. These outer rise faults are either reactivated from a pre-existing mid-ocean ridge fabric or in some cases new faults form. We're pretty sure these faults penetrate well down into the mantle portion of the downgoing plate. This is a result from Facenda et al. 2009, which illustrates this. In this case, faulting in the outer rise region is penetrating almost 30 kilometers down from the moho into the middle portion of the slab. And the distribution and magnitude of this faulting is important because it's controlling weakening in this region. So why is the weakening important? Well, there's a potential feedback mechanism going on. As soon as you have faulting in the outer rise that leads to slab weakening, now the effect of slab weakening is to potentially modify the amount of slab pull force that is transmitted into the upper surface plate. As soon as you modify the amount of slab pull being transmitted upwards, it can modify the plate velocities, which in turn then modifies the larger scale dynamics of the subduction system. As soon as you modify the dynamics of the broader subduction system, it can then go back and affect the faulting. So it's important to keep in mind this feedback mechanism that's potentially going on. So in this talk, I want to address 3 primary topics while keeping that in mind. The first thing I want to talk about is the primary controls on outer rise faulting patterns. The The second thing we're going to talk about is the effect of brittle strain weakening on the total slab strength. And if I have time, I'll talk about some future directions for modeling outer-rise deformation in the Tonga system, which we've just started. So first, the primary controls on outer-rise faulting patterns. We're going to examine these in a model of oceanic continental subduction. The model is 200 kilometers deep by 2,000 kilometers wide. It's free slip on the top and sides. It's an open bottom boundary. On the bottom, I'm showing the initial compositional structure, and what's separating the oceanic plate from the continental plate is a weak pile of sedimentary rocks, and so this is analogous to an accretionary prism. We're constantly driving subduction in these models with an applied velocity boundary condition, and so this velocity boundary condition throughout the model run is constantly pushing the slab down beneath the overriding plate. The rheology in the model, which is really one of the key aspects of this, is viscoplastic. It's a non-Newtonian viscosity combined with a plastic Drucker-Prager type rheology. Now it's that plasticity that's going to allow for localized deformation in the bending portion of the slab. We are going to limit the viscosity in that region and localize it through a yield stress. The yield stress is equal to the friction coefficient here times the dynamic pressure plus the cohesion. We're to consider two values of the friction coefficient, a strong value for low values of strain, and then a weaker value for when the strain is greater than 1. I'll talk a little bit later in the talk about what the effect of varying those is, but for now we're going to stick with these values. So, how do we analyze outer-rising faulting deformation patterns? Right here, I'm showing a snapshot of deformation in the outer-rise region. The green bands are low viscosity normal, are analogous to low viscosity normal faults. The top black curve is a curve through the moho. The lower black line is a curve parallel to the moho and 3 kilometers beneath it. The way we're going to quantify the outer-rise faulting patterns is by analyzing the viscosity structure along this lower line. So each one of the blue stars represent one of the faults in the model, or they represent the minimum viscosity within that faulting zone. What I'm showing on this bottom figure right here is the horizontal position, and then on the y-axis, it's the log of the viscosity along this lower black curve. At each one of these minimum points, it's the center of one of the faults. And so what we do for each model and each time step is we systematically go through and count each one of these faults. We identify their location and their viscosity. And once we have these values, then we can go through and start looking at faulting properties like the fault spacing, the total extent of the faulting region, and the number of faults within this region. If we want to do some systematic analysis, we need to sort of have a cutoff for the maximum fault viscosity that we'll consider. Here's an example. If I have a maximum fault viscosity of 10 to the 23 Pascal seconds, if this is the cutoff, then in subsequent analysis, I'd only consider fault values beneath this cutoff. So what are some of the primary controls in outer-rise faulting patterns? The first thing we're going to look at is downgoing plate thickness. So what I'm plotting on the x-axis is plate age in each one of these subfigures. And on the y-axis, I'm plotting the lateral faulting extent. Here it's the number of faults. Here's the fault spacing. And here it's the maximum depth of faulting, or in other words, the depth to the maximum depth that the faults penetrate to. The individual colors represent the different maximum viscosity cutoffs. And so what you see is if you use a low enough viscosity cutoff, is that as you increase the plate age and the thickness of the plate, as you start to see this trend up to around 80 million years where the total extent of the faulting area is increasing and also the number of faults is increasing. Interestingly, the fault spacing after 30 million years, it's staying constant. If you look at the maximum depth of faulting, it's corresponding to the lateral faulting extent and number of faults, where up to around 80 million years, it increases and then it levels off. I'm not going to show these results, but in terms of if we looked at the convergence velocity, we see a similar trend. The lateral faulting extent and the number of faults both increase as a function of the convergence rate, but the fault spacing stays constant. The take-home point here is that an increase in the mechanical thickness is leading to an increase in normal faulting in the outer-rise region and total deformation. Now I'm going to look at something fairly interesting, downgoing overriding plate coupling. And before I show you this figure right here, ignore that for now. It's a little shocking, but I'll get to that in a second. So I'm going to look at two models here. I'm going to call it coupled and uncoupled. In these models, I increase the model base depth to 600 kilometers. And what ends up happening is you end up getting much stronger corner flow and rapid weakening of the overriding plate in these models. In the top model, I call it a coupled system because the downgoing plate is still connected to the continental plate through this weak accretionary prism. What happens eventually, if you let the model run long enough, is the overriding plate starts to break up, and you basically get this large low viscosity zone that's separating the accretionary prism, the downgoing plate, and the continental plate. What happens as soon as you start to have this basically uncoupled system is that the amount of total deformation in the outer edge increases dramatically. You have more faults and you have more total weakening. So in the real Earth, I don't think there's any example where we're having this much decoupling between the slab and the overriding plate. But this is just to illustrate that the amount of plate boundary coupling, if you decrease that plate boundary coupling, it's going to lead to an increase in the amount of normal faulting, a significant increase. So the next thing I want to address is the effect of varying strain weakening magnitude. I'm going to look at this for both coupled and uncoupled systems. So the strain weakening magnitude is basically the difference between the initial friction coefficient and the weakened friction coefficient. For small values of strain weakening magnitude, you would expect a large number of faults that only accommodate a small amount of deformation. If this value is large, you would expect fewer faults, but each one of those individual faults is going to accommodate more deformation. So what I'm plotting here is the effect of strain weakening magnitude for both coupled and uncoupled subduction systems. I'm looking at the lateral faulting extent, the number of faults, and the fault spacing. There is a trend here, and the trend is that there is absolutely no relationship that we're seeing between the strain weakening magnitude and any of these faulting properties. It was really, really surprising. I'll address this later, why we're not seeing a trend. But the thing to take away from this is there is no trend in faulting patterns with the varying strain weakening magnitude. So now this is a value. I'm going to look at the actual total reduction in viscosity in the trench region. This has implications for the amount of slab pull being transmitted up through the plate. So what we're looking at again is the strain weakening magnitude for both the coupled and uncoupled subduction systems and how much the viscosity in the trench region is being reduced. In the coupled subduction systems, we're seeing about a reduction of 20 to 25 times. In the uncoupled subduction systems, you see a much, much larger decrease, anywhere from around 60 to 175 times. Again, I don't think these uncoupled subduction systems are realistic, but I just want to emphasize how much the coupling at the plate boundary is affecting the total reduction in viscosity in this region. If you were to apply this to the actual Earth, I would think these values are much more reasonable in terms of what you could get. So now I'm going to make an analogy to Tonga. I'm going to switch gears a bit. Instead of modeling oceanic continental subduction, we're going to switch to oceanic subduction. And we're going to switch from a viscous plastic rheology and add in elasticity. The code I'm using here is from Fresenda et al. 2012 G-cubed. And so our model setup is a 90 million-year-old downgoing plate and a 10 million-year-old overriding oceanic plate. What we do is we apply a convergence velocity of 20 centimeters per year for 2 million years, and then after that, we remove the condition, so the model is dynamic. And again, what we're looking at here is the strain weakening magnitude, so the difference between the strong coefficient of friction and the weak value. That's the value I'm plotting here. So for the small values here, we're actually seeing an effect of the strain weakening magnitude. At the low values, we see a large number of faults, but each one of those faults is relatively strong. It doesn't accommodate a lot of deformation. But then for the higher values, we strongly localize deformation on just a few faults. So the question to address here is how much is this affecting the trench viscosity? The answer is not at all. What happens is you vary the strain weakening magnitude. There's effectively no change in the total amount that the slab is weakening in the trench region. And so this was a bit surprising too. So to conclude the first part of the talk, the thing to take away from this is that outer rise faulting patterns are strongly sensitive to the plate age, the convergence rate, and the downgoing overriding plate coupling. In these models, the brittle rheology is exerting significantly less control on the faulting patterns and slab weakening in these oceanic continental subduction systems. And this is largely due to the rapidly evolving overriding plates that I think is effectively swamping out the signal of the varying rheology. And so in terms of that, the faulting patterns and slab weakening values that we're seeing, they reflect the overall stress rate and strain rate of the system rather than the actual brittle properties of the downgoing plate. In the oceanic models, we actually saw that the faulting patterns did vary somewhat on the brittle properties, but then the slab weakening values did not vary at all on it. And so then to conclude, the regional models, if we want to start carefully assessing their relationship between the total amount of weakening, the normal faulting, and the brittle strength of the slab, we need to go to regional models to carefully assess these patterns. And what I want to leave you with in one slide, So what our ongoing work for Tonga right now is, rather than doing these long-term dynamic models, is we're going to input the upper mantle slab structure from slab 1.0 into our model, and we're going to have a plate boundary structure that's defined. This is an example from Contreras-Reyes et al. 2011. This is an example plate boundary structure from the Tonga region, and our plan is to compare this to outer rise faulting pattern seismicity and slab weaking. The final slide I'll show you is all of this is the outer rise earthquakes since 1988. And this right here is the faulting patterns in the Tonga region, at least for one section of the Tonga region that undergraduate student Jesse Saunders at Davis has been developing. And so our hope is that in these regional models, we'll be able to get much tighter constraints on what the rheology of the downgoing plate might be through comparisons to the faulting patterns and the seismicity. Thanks.
Do we have time for a quick question? Okay. One from Claudio.
Yeah, sometimes you observe also reversible in the outer rise.
Yeah, well, in terms of the seismicity? Yep, so that's the big question. So then none of these, all these models, our normal faultings are simply terminating at the midplane, and we haven't been able to get any deformation, or at least any brittle deformation in the compressional area. I've seen some results from Manuel Facenda where if you add in a piral stress, if you vary the piral stress, you can actually start to get some deformation in that region, but I'll need to carefully examine that to actually see what the values are of that. So that's the only way I've seen that you can actually get deformation in that part of the slab in the compressional. It's kind of a mystery, yeah.
Okay.
Okay,
Thank you.
thanks.
Thank you.
We can proceed to the next one. We have two more from Gianpiero Iafaldano. And the title is The Strength of Large-Scale Plate Boundaries, Constraints from the Dynamics of the Philippine Sea Plate since 5 million years ago. Please.
You've got that.
Yeah, it's yellow.
Yellow is at 11, or this is going to count down. It'll
Yep.
be at 2 minutes.
Okay.
It'll go yellow, and then at 13 it'll go red.
Thanks. So I've had the fortune in the past to have numerous opportunities for long-term interaction with the field and structural geologists. And what I've learned from that is that one outstanding question in that community is what's the strength of crustal faults? And I think that's a relevant question to the geodynamics community as well. What's at the larger scale of plate boundaries, at the larger scale of the whole lithosphere, what's the strength of plate boundaries? Because that has implication, of course, for the kinematics of plates and for the dynamics of plates. And so what I would like to show you today is some inferences that one can derive from the dynamics of the Philippine Sea plate over the past 5 million years. This is a figure that I like to use a lot. It shows the strength profile for mostly oceanic plate boundaries, but the inferences that I'll make are true for the continental plate boundaries as well. The strength is basically the stress to overcome in order to have to initiate and sustain sliding between plates, and it increases linearly with the overburden pressure in the upper portion of the lithosphere. That's the brittle part. And then it decreases exponentially with temperature in the lower part. That's the ductile portion. And that's the result of numerous experiments performed over decades. The point that I want to make is that at the scale of plate motions, of course, what's relevant is the integral of that profile. That's the total stress one needs to overcome, again, to have relative motion between plates. And that's shown in dashed here. So that curve tells us how much of the total strength in relative terms has been built up to a certain depth. And the point here is that 70 to 80% of it actually is hosted within the brittle portion of plate boundaries. And that inference is true regardless of the strain rate, regardless of the temperature, within the ranges typical of plate tectonics. The difficulty, so when one looks at this type of profiles, it would seem logical then to assume that the friction coefficient, which is the slope of the brittle profile, is the parameter to prefer to give a key indication of what's the total strength of plate boundaries. But the difficulty is really to put a number to the friction coefficient. And so that's really what I wanted to address today by looking at the dynamics of the Philippine plate. This is a reconstruction of a global reconstruction from the group of Dietmar Müller in Sydney, and I would like you to focus within the purple circle. That's the Philippine plate. Motion has been predominantly northward up to 5 million years ago, and then it switches westward. And we don't know why is that, but we know that that's overall that marks the initiation of subduction of the Philippine plate beneath Eurasia. So motion has been predominantly westward within over the past 5 million years. And so, because it's only 5 million years then, it's logical to think that the Philippine slab hasn't reached the deep mantle yet. In fact, it's imaged through seismic tomography not to have reached even the 410 transition zone. So it's the slab tip is down to 200 to 300 kilometers. And so presumably then the slab pool, the net slab pool arising from such a small volume of slab attached to the trailing plate is small. Yet when we look at the kinematic record, the Philippine plate is one of the fastest moving plate at the present day. And here I'm showing the longer term record over the past 5 million years and in comparison with the Pacific plate. And the lines here at 0 million years, that's the snapshot, the geodetic present day record. So the question is then, if the slab is so small, if the net slab pool is presumably small, what drives the Philippine plate at such high rates? And that's a question that has been addressed in the past. Tetsuzo Seno, for example, inferred that the torques associated with the small slab volume attached to the Philippine plate wouldn't be enough, even when combined to the torques associated with plate thickness variations, wouldn't be enough to drive the plate at the observed rate. And so the logical inference to me is then it must be a result of frictional forces imposed on the boundaries of the Philippine plate. And so here I'm showing this in a concept cartoon, if you want. There's some frictional stresses imposed by the subduction of the Pacific plate on one side, and they have, of course, a tangential component, which is shown in red, and these are the driving stresses. And these are resisted by similar stresses on the other boundary where the Philippine plate subducts beneath Eurasia. And of course, these are also resisted by mantle drag, which presumably in terms of mantle flow is dominated by the subduction of the Pacific slab here. So in simple words, the Pacific plate is pushing westward the Philippine plate, and this is a mechanism that is resisted by friction along the Philippine-Eurasia margin and mantle drag, and the friction coefficient controls the efficiency of this mechanism. And so the problem that I want to pose is really an inverse problem. To me, the question is not whether friction can drive this mechanism or not. It's in a way clear that it has to be the case, simply because there is no other reasonable hypothesis to explain the fast motion of the Philippine plate. So the real question is then, what values do we need? What's the friction coefficient that we need in place to allow such mechanisms to be so efficient to drive the Philippine plate at the observed rate? And so that's the question that I want to address. And it's a relevant question when we look at it in the context of other measurements. The classical example is the Barley's law from laboratory experiments. The friction coefficient should be between 0.6 and 0.85. But when we look at, for example, at heat dissipation from the San Andreas Fault Observatory depth, we end up with an upper limit of 0.3. So already more than twice less than the prediction of the Barley's law. More recently, John Sappi has shown that when you look at the geometry of critical tapers, you can infer a coefficient of friction of less than 0.1. That paper actually is a pleasure to read, and it's very powerful because it allows basically to infer the friction coefficient simply from reflection seismology, for which we have a lot of data. And even more recently, the work of Giulio Di Toro at INGV showed that even at the co-seismic slip rate, again, very low value for the coefficient of friction. So it makes sense to ask the question, at the larger scale of plate margin, what's the coefficient of friction? One thing we know is that the sediment, the sedimentation of the ocean floor, and presumably the amount of sediments that enter the trench have an effect, and that's a key control because they have a lubricating effect, basically. And so this is a map showing the present-day sedimentation of the plate boundaries of the Philippine plate. we can take this picture as true over the past 5 million years at least, mainly because these sediments come from the discharge of the Yangtze River, which has been in place for the past 40 million years at least. And so what they show is that the margin between Philippine and Pacific is sediment-starved, and therefore presumably the coefficient of friction is larger there compared to the margin between the Philippine plate and the Eurasian plate, where there is a lot of sediments. So that's what we know about sediments. Again, the problem is to put a number to those inferences. And so here is where I have to make assumptions and to test those assumptions. So this is really a test for the relation between the sediment above oceanic margin and the coefficient of friction. And I will assume that the relation is linear, simply because that's the simplest assumption I can make. And the coefficient of friction decreases from a maximum to a minimum with increasing sedimentation of the ocean floor. The maximum and the minimum are, of course, already 2 parameters in my problem. And then I introduce a third parameter, which is a saturation thickness, the thickness of sediments over which the coefficient of friction doesn't vary anymore. And the physical reason for that is because it's plausible to assume that at some point the sedimentation is so large that it becomes either irrelevant or impossible to reduce any more the coefficient of friction. And so that parameter, the saturation thickness, basically serves the purpose to parameterize our ignorance on how much sediments is too much in that process. When one varies those 3 parameters within reasonable ranges inferred, again, from independent evidences, mainly, again, from structural geology, you get an idea of the number of what I call frictional models that can be tested. And in this case, these are on the order of 100, in excess of 100. So what I will do in the following then is test each of these models and test how much they can explain the kinematic record of Pacific and Philippine plate. And to do that, I'll use global models of the mantle coupled with lithosphere models. These are basically the Terra code for the mantle and the shells codes developed by Peter Bird for the lithosphere. I don't have time to go through the detail, but I'll just mention that the coupling serves the purpose really to account for all the components of the torque balance, including buoyancies from the mantles, which lithosphere models don't know anything about in principle. The structure of the lithosphere and the configuration of plate boundaries is explicitly included within the finite element grid, and you see a snapshot here. So this is the Australian plate, and the Philippine plate is here. All these boundaries, all these faults feature a different coefficient of friction according to the friction model that I want to test. And the outcome of these models is Euler vectors for each plate. So in particular, I will look at the ones for the relative motion of Philippine and Pacific plate with respect to Eurasia. So since it's a 3-parameter problem, what I'll do is I'll fix 2 of them and I'll vary 1. And the dynamics is better explained in that sense. So here I'm fixing the minimum coefficient of friction in the model, the saturation thickness, and then I increase the maximum. Of course, the efficiency in driving the Philippine plate increases for increasing maximum friction, and that makes sense, right? Because again, the margin between Philippine and Eurasia is the one yielding the lower friction of coefficient, as opposed to the one with the Pacific plate. At the same time, and this is really by virtue of 3rd Newton's law, the Pacific plate motion also decreases to a minor degree, of course, because it's a larger plate, so it's difficult to overcome mainly basal shear stresses from such a large area. And so in assessing which of these frictional models are in fact matching the data, I require that both plate motions are matched within the error bars. Here you get an idea of what happens when we also vary the saturation thickness. Of course, the larger is the saturation thickness, the less is the resistance that the larger is the saturation thickness, the more is the less is the resistance that the Eurasian plate exerts on the Pacific, on the Philippine plate, and that's why we see this trend in the convergence of the Philippine plate. If you prefer to look at convergence, then here is also a match with the direction of convergence. But what I prefer is really to look at the position of the Euler vectors, and these are plotted here in C and D. So the dots are the position of the Euler pole, and the color is the angular velocity. So out of all the frictional models that I've tested, these are the only 3 that yield a reasonable agreement with the observation. And the good news is that the 3 of them agree with each other. So it means that within the range of these models, we can constrain, in fact, a relationship between the lateral variation of friction coefficients and the sedimentation of plate margins. Of course, it remains the question why friction coefficients of larger scale plate margins appear to be so low compared to laboratory experiments. This is my last figure. If you want, this is a snapshot of the budget of forcing in place along the margins of the Philippine plate. So the color here is basically the coefficient of friction, which again is the preferred parameter for the strength of plate margins. 2 points for which I have no time, but I'm happy to take questions. The increase that we see in the convergence of the Philippine plate from the paleomagnetic record to the geodetic record can be well the result of a matured slab. The volume of the slab increases towards the present day, and therefore we see that in an increase by 1 centimeter per year in the convergence of the Philippine plate. And the final point is that this is not incompatible with extension that is observed in the Mariana Trough. Again, I have no time to go through the details, but I'm happy to take questions. So I hope I convinced you that there are lateral variations in the coefficient of friction, and these are predominantly controlled by the sedimentation of the ocean floor, which poses a problem, right? Because it means if we want to understand in detail the past dynamics of plates, then we also need to reconstruct the past sedimentation of the ocean floor. Thank you.
Thank you. Okay, time for one quick question. Questions? Okay, thank you.
Thanks. In this case, we proceed to the last talk, which is from Rebecca Farrington. Co-authors are Capitanio, Moresi, and Stegman. The title is Contributions to Dynamic Topography from Shear-Driven Mantle Flow at Lithospheric Edges.
Black button right there.
Oh, cool.
Okay. This is going to count down when it gets to 2.
Yep.
Then it goes yellow when it gets to 0.
Okay, cool. Okay, thanks for staying. I'd just like to start off with going through a few of, I'll just set the scene and talk about a few fairly straightforward observations. So to start with, the continents have an inherently 3D structure. I feel this figure shows this very nicely. It's from Fishwick et al., 2008, looking at the Australian continent, and we can see that there's these distinct tiers in the depth of the continental lithosphere. Okay, and also this is a figure showed earlier from Maria Seaton's work this year, that plates move. So just to highlight again, I mean, this is obviously not the current configuration. And tying these 2 points together, there's a demonstrated relationship between continental morphology and plate motions. And this is some work from King and Anderson in 2008. This has been a fairly popular field of research, and I thought I'd just have a look at some fairly early work. We wanted to have a look at the interactions between the plate motions and continental morphology through some numerical models. So what we've done is have a look at continental morphology in a uniform block morphology as well as a tiered morphology. So this is a cross-section, so you can see this one kind of approximates the Australian continent. And we also wanted to have a look at how that interacts with different plate velocities. So in the models we had plate velocities of 0, 2 centimetres per year and 20 centimetres per year. I've got a rigid continent placed within actively deforming, convecting upper mantle. We've imposed the boundary conditions using Couette flow. So we've got periodic boundary conditions on the side walls and mirrored on the front and back. The thermal initial condition is a quasi-steady state thermal condition, which ended up being an insulating continent, which provides the hot subcontinental mantle Adrian Lenartic's work in the previous session kind of showed what the two-dimensional analogue of that was. And the runtimes for the models, we took it as a time that it takes for the continent to move from the central position out to the side of the continent. But before I go into the... Sorry, I used Underworld to solve these models. Before I go into the final results, I just want to take a step back and have a look at some of the contributing factors in the end results, because they do get quite complicated. So looking at just a lithospheric step in a kinematically driven like plate velocity model, there's no buoyancy here, either thermal or density driven, compositionally driven, sorry. So the first figure here just shows the velocity magnitude with the continent moving this way. And as you can see, with the pressure, you get pressure gradients caused by flow going into this contraction, which is a negative pressure gradient, and a pressure gradient out into the expansion as a positive pressure gradient. So these lateral pressure gradients lead to dynamic topography. And so we get a tilting in the surface of this block from looking at the vertical stresses. And the magnitude of this tilting is dependent on the step height. So for this step height that I've shown up here is the red line, and for successively smaller steps, it linearly decays. The magnitude of that surface stress or topography is also dependent on the plate velocities. So if we include a thermal anomaly into the equation, so this is looking at the thermal anomaly in isolation, we have a 10% pressure increase here, followed by a decrease here. These are just instantaneous models. We can see with the plate moving through time, with the hot thermal anomaly directly underneath the continent, which is similar to what you would get if the continent had been stable for a long period of time, like with the supercontinent setup. You get a large dynamic topography signal right in the centre. As the continent moves off the thermal high, you see with B, the transition period, and then with C, it has a topography low. So in our models, this is all happening with a background thermal convection. So if we have this insulating continent with the normal thermal convection, we get a quite pooled mass of hot mantle underneath the continent. Looking at the pressure gradients again, we can see pressure gradients linked up to the surface topography. And while we have the smaller scale signals that are on the scale of the convection cells, we also get this tilting in the continent caused by simply the thermal pooling of the hot mantle underneath the continent. So just to be clear, in this case, there's no plate motions. It's just a closed, no slip boundary conditions on the top and bottom. Okay, so taking these all together, I'll present a final flow field models. These are for the uniform continent, so looking at a bird's eye view, looking top down into the continent. We've got some streamlines. I placed particles here at the top, the left-hand side. The streamlines are coloured with vertical velocity, so you can see where things are upwelling and downwelling. So blue is where it's going down, and red is coming up. So when we don't have any plate velocity, we have just the thermal model. So this flow field is controlled by just the thermal convection, and you can see the extent of the three-dimensional aspect of the resulting flow. So we get flow in both lateral directions with, for example, it's kind of hard to do a 3D kind of swirl with my pointer, but you can see fluid comes up and is pulled down and up and underneath the continent with the hot upwelling and then flows out. At the other end of the scale, when we have a 20 centimetre per year plate speed, which is quite high, we get really just a plate shearing model where the resulting flow is really just what you would expect from a 2D model of the continent is just riding over top of the mantle underneath. And we just get these broad downwellings and upwellings. So these first two cases, we have the two polar extremes, where one is driven just by thermal convection and the other is just driven by plate motions. So in the centre, when we have a realistic plate speed of 2 centimetres per year, we can see that we start getting this corkscrew flow effect, where material is going down at a distance away from the continent, swept underneath the continent and up, and then out through this direction here. So what's interesting just to point out as well is that in the 3D cases, we have the pressure gradients in both lateral directions, whereas in the earlier two-dimensional models I showed, we only had them in the one. So we do really get that three-dimensional corkscrew flow. When we step through to the tiered continent morphology, with the tiers coming out this way, so a successively shallower continental lithosphere, the flows you can see is really controlled by this morphology, where as the continent is shallowing out in one direction, the mantle flow just follows in that direction. And that's related to the pressure gradients, the lateral pressure gradients again. For the high plate speed models, there's really no difference. It's still controlled by the plate motion. And for the moderate plate speeds, we can see that we have, again, a continental morphology controlled, where we have quite a bit more of the lateral motion. So if we have a look at the dynamic topography within the continent caused by this flow, in this top box, the red box is just all that we're looking at, so it's only the continental topography for the uniform and the tiered continental cases. With no plate velocities, we can see that we have dynamic topography on a spatial length scale similar to the mantle convection that we were seeing, and on scales of a couple hundred metres plus or minus. When we bring in the plate velocity of 2 centimetres per year, we can see that that dragging, the shearing, is causing some basins to be formed at quite a distance inland from in the continent. And with the plate shearing model, we really don't see a great deal of change in the flow, in the topography, sorry. But what's interesting is for the tiered model case, even when we don't have the plate velocity, we still have these quite deep, deep topography, so the basins forming within the continent at those edges at depth. And once we increase the plate velocity to a realistic plate velocity, we get quite deep basins. Okay, the figures are a little bit grainy. I've just plotted the nodal values, so I haven't been interpolating within the element volumes for those. Okay, so in conclusion, we found that the morphology of the continental plate at depth is important. And it's fairly interesting that it's whether you have a plate velocity or not. Obviously, having the plate velocity magnifies that effect, but even at the steady state, or the zero plate velocity continental morphology, it makes a difference. So the 2D versus 3D, so we can see that the mantle is moving at normal to the direction of plate motion, which is something to consider as well for kind of these larger scale regional models. And we see that deep continental basins can be formed as a consequence of continental basal morphology, and those can migrate with time depending on the plate speed and the duration of the model. Thanks. I finished early.
Okay, thanks a lot. Are there questions? Yeah.
Yeah, I stripped out the lower frequency wavelengths in the dynamic topography plots that you saw. So I took out the, I think, larger than 500 kilometres. So I did already take account to that, but not specifically for the strength. Yeah.
Other questions? Okay, thanks a lot for coming to the session. Don't forget about the poster session tomorrow afternoon.
Okay.
Thanks a lot.
Thanks for presenting too.
Yes.